Good morning, everyone. So this is a practical exercise that I will solve here. Of course, it will be important for you at some point to pause the exercise to make the calculations, because I'm not take the same methodology we have on the classroom, where I can wait a bit so you can make the calculations. So I will say to you, okay, pause the exercise and try to solve the calculations and so on. So as you probably noticed, this is taught in English because we have some fellows, Erasmus fellows, that are at home. They are forced to stay at home. They got the flu. So for the Portuguese fellows that have some issues with English, um, please ask me by email if you have any question. Ok, pessoal que fala português e não percebe bem inglês, depois falem comigo se for necessário algum esclarecimento. You can see that the assignment is in Portuguese, but anyway, you can easily get it by the context. This exercise is not on the exercise sheet you have on the e-learning platform, so it's two different exercises, so you still have some material to work on the practical classes. And the objective here is to play a bit with the Cauchy formula equation and to get familiar with the two different ways to represent the stress state in a point. So what we have here, it's given the stress Cartesian components of the stress tensor, the stress matrix we saw on the theoretical part. So you may want to take a print screen of the exercise so you can easily follow. So I will push this a little bit to the side so we can write down here the stress tensor. Put the pen here. Okay, so the stress tensor, it's a 3 by 3 matrix in the way we use it. We usually work on megapascal, that's Newton per square millimeter. And on the diagonal of the matrix we have the normal components, x direction, y and z. Okay, and outside the diagonal we have the shear components. And as we discussed on the theoretical class, so this is yz, it's over here. This matrix is symmetric. Okay, so I will not bother to write here 50, 60, minus 75. I will just say, okay, this matrix is symmetric. And then what's asked to you on the A question is to calculate the two vectors, normal and shear vectors, that comes from the definition of the vectorial resultant stress. So I will make the same drawing you saw on the theoretical class. So we can cut any solid by a plane, and this plane shall be defined by a normal vector. Okay, so from algebra you know that every plane shall be defined by a normal to this plane, and this normal vector has three components that are called the director cosines, or something like this in English, cossenos diretores in Portuguese. And we know this is a versor, so it's a vector that has a modulus of 1. So we know that this relation holds. Okay, so the modulus of the vector shall be 1. And this will be important here because, as you see, we have here the definition. Alpha is gives us the first cosine, and beta gives us the second. So that means we know L, that is the cosine of 68 degrees, and we know M, that is cosine of 35. Yeah. And so we need to determine the third cosine, and that will be following this relation, 1 minus square L square M. Okay, so this is the part in the class where I ask you to perform these calculations. So you may want to pause a bit this video and make the calculations now. Okay, and you are coming back, I hope. Don't aldrabate this. Não sejas aldrabão. Sorry, guys. The non-Portuguese will not understand this. Okay, so let's put here the results for the cosines. And the third one from the relationship will be 0.434. So you can always feel free to correct me on the comments of the YouTube video if you see that some calculation is wrong over here. So now we have the definition of the normal vector. We know the normal direction of the plane we are working. So let's just remember that our resultant stress can be in any direction, given that is depending on the forces acting on the solid. So this is a solid that is in equilibrium, so we cut and we check what's going on inside the body that promotes the equilibrium. So, and of course we are analyzing an infinitesimal point, and so the resultant stress is nothing more than the resultant of the forces acting on that point divided by a very small area, an infinitesimal area. So this is the definition of stress, and that's why it's force by area, that this area is tending to 0. But anyways, the measurement is given in Newton per square millimeter. That's the same unit as pressure, but the stress is the same. So I am able to decompose this resultant stress into two components. So now we have here this decomposition that will be our normal vector, and we have the shear component that's perpendicular to the normal vector. So we always know that this vectorial relation holds. Okay, so the resultant stress is the sum, vectorial sum of the shear, normal and shear components. So the first question is then about defining both of these vectors, but of course to define these two guys, first I need to define the resultant stress, and to do that we are going to use Cauchy formula that we saw on the theoretical class, that says to us that if we know the stress tensor, and we know it, and if we know the normal vector of the cutting plane, sorry, my mistake here, you see I'm trying to put my hand on the screen and this is not good. Okay, so this is the normal vector, so this is 3 by 1 in terms of dimension, 3 by 3, 3 by 1. So this is consistent, okay, in terms of size. So we know the orientation, we know the stress tensor, so let's make some matricial calculations, matrix vector, and then we can get the 3 Cartesian components. Of course, this whole exercise is in a referential XYZ typical one. So let's promote this calculation over here. So once again, we are going to multiply that matrix we defined by the vector that is consisted by the director cosines. I really hope this is the correct English name for that. So this matrix is symmetric, okay, don't forget about it. And so let's use these 3 values over here, okay. So 0, 375, 0, 1, 19, 0, 4, 3, 4. Okay, so you show pause this now, perform the calculations, get used to make this kind of calculations in your calculator machine. If it's a Casio, a Texas Instruments one, get used to it, because it's quite important that you know how to do it and how to do it fast during the exam. So if you pause it and you solve it, and now I will put the results over here. So everything still in megapascal, and we have the 3 components of the stress vector, megapascal, right? Okay, now we have the resultant stress, and now I'm going to make the decomposition into the 2 components of the stress. And the easiest way to do it is to use some algebra. And from algebra, you know that if you want to project one vector into another direction, all you need to do to get the size of this vector is to make what we call the internal product between 2 vectors. So what I'm trying to say here is something like this. Let's change the color, we have plenty of colors. The modulus of the normal vector is obtained if I make the internal product of the resultant stress and the direction of the vector I want to get the modulus. So we know that the normal vector, normal stress vector, is in the direction of the normal vector to the plane. So I know once again everything here. So you must remind that the internal product is obtaining multiplying the x component of this vector with the first component of this vector plus the second components plus the third components. So that will be 96.7 times 0.375. Forgive my handwriting, I'll try to get better during the semester. And finally, these 2 guys over here. Okay, once again, pause, make the calculations, and you are going to get the modulus of this normal vector. Okay, so far we know the size of this vector, but to define the vector completely I need to know the 3 components x, y, and z. And once again, if you remember algebra, we know that if you know the modulus of one vector, in order to obtain the components in the referential, all we need to know is the cosine directors of that direction, and we know it. Okay, so now I'm going to decompose the normal vector into the three components. Okay, and if I perform these calculations using the values we got on the beginning of the exercise, so these three cosines will allow us to decompose any vector that belongs to the normal direction into its components. And so I have the calculations, of course, and you may want to pause, so you want to practice a bit calculations. And here we have the three components of the stress, normal stress vector. So in order to finish this first question, we also need to obtain the shear stress vector. Okay, and this is quite easy because, as you could see here, we know that the resultant stress is vectorial sum of the normal stress and the shear stress. We have already both of these guys, so that will be particularly simple because I can just say that the shear stress is going to be the resultant minus the normal vector. Okay, so let's change a bit the color, and so I just can say that tau x, tau y, and tau z will be the difference of the components we already calculated on this exercise. Okay, guys. And so, once again, so this is really simple calculation. So we are gonna have here 46.4, 7.3, and minus 53.8. Okay, so this is going to solve the first question. So now let's check the second question. Sorry, this computer is quite slow. It's a refurbished tablet PC, which is not bad anyway. It's old. So the second I will leave to you. This is quite similar. So the second question is to get the orientation of the both vectors we defined previously. And guess what? We already know one of the two orientations because the normal stress is actually in the direction of the normal vector. So the orientation is basically the one we already have here. Okay, so this is answer. And for the tau vector, the shear stress vector, we don't have it, but if you remember algebra, it's not that difficult. So let's first state here that the orientation of the normal vector is coincident with the normal stress vector is coincident with the normal vector that defines our cutting plane. But for the shear, this is algebra again. If you divide each of the components we calculated over here, so this is valid for any vector in space. Okay, so if I divide each of these three components by the norm, or by the modulus of the vector. Then we have the three cosines that define the orientation. Once again, you can make the calculations by yourself, and in the end it will result, this will be the L tau, the second one 0,10 will be the M tau, third one okay. So this solves the second question. So guys, I hope that could be clear enough for you. Any questions? You have many different ways to contact me or any of your practical classes teacher. Okay. On the practical classes, similar exercises will appear as well. Okay. Take care. Have a nice weekend.